Hello, hope everyone's doing well. So we are finishing up chapter 6. We've done most of the naming. Well, we've done all of the naming stuff. So hopefully you guys ladies are comfortable with the naming. Let's share a screen here. So do know that this chapter, in these set of slides, do omit 6.7. Okay, section 6.7 of this is like all the Lewis dot structure shapes, like trigonal planar, tetrahedral, like all the molecule shapes. You won't need to know how to do those. So if you are bumping into the textbook and you're seeing, oh, there's this whole chapter 6.7 and we haven't gone over this, that's not going to be covered on an exam. So you can just ignore that. So make a note somewhere that says 6.7 is not your responsibility. You're looking for the video from 10.5. I don't think I've put it up yet. I'll put it up after today, or after class today. I'll get it up for you, Courtney. All right. Perfect. Okay. So when looking at a periodic chart, there's a couple different trends that we see on the periodic chart. One thing has to do with size, right? So the biggest guys are down here, smallest ones are over here. Another one has to do with metallic quality. So most metal-like thing is down in the lower left, least metal-like upper right-hand corner. And then another thing is the electronegativity. And electronegativity is pretty much, it's an arbitrary number that they set off of fluorine. Fluorine is 4. This number doesn't have any units to it. It's just all in reference to that. So fluorine has the highest at 4. Oxygen is the next highest at 3.5 and then 3. You will not have to have these memorized, these electronegativities, but you do need to know their importance. So electronegativity is, you know, how, kind of think of it as how greedy is something for an electron. So fluorine has a really high electronegativity because it loves electrons. Why did we not include group 8 here? Do the noble gases want electrons? No, they're satiated. They already have an octet or a duet, so they're good. So we keep it at fluorine as the highest. So he is the greediest one on the periodic chart for an electron. The least greedy are the stuff in the lower left-hand corner. Why? Well, because they only have 1 or 2 valence electrons. It's much easier for them to give the electron up than it is to hold on to it. And as we move down, the atoms get bigger. And as they get bigger, their electron shells get bigger. So you can kind of think of it as like an onion layer. That outer onion layer, if you've got like 6 or 7 layers, that outer layer is really easy to peel off. So it's real easy to grab electrons from big guys like this. Much harder to get them from tinier things because the electrons are closer to the nucleus. So they just, the protons will hug onto them more. So why do we care about electronegativity? Well, electronegativity, specifically the difference in electronegativity, will let us know what type of bond we are creating. So we can have nonpolar and polar bonds. And the nonpolar covalent bond, so this is a bond, remember, covalent means that we are sharing the electrons. This is also sometimes called a molecular bond. These are between two nonmetals. In a nonpolar covalent bond, such as H2, electrons will be shared equally. Okay. So hydrogen, if we go back to this chart, hydrogen has an electronegativity of 2.1. So we can classify its greediness as 2.1. Well, if it's hydrogen and hydrogen, we can say that they're both equally greedy for those electrons, right? So they share them right in the middle. So we call that nonpolar. Polar means that there's some sort of asymmetry to it. So in this case, nonpolar, there's no asymmetry, equal balance. In a polar covalent bond, which happens between two nonmetals that are of different electronegativity, the electrons are not going to be shared equally. Now, what we can see here is that, let's go back to the periodic chart. So hydrogen has an electronegativity of 2.1. Chlorine has an electronegativity of 3. So chlorine is greedier than hydrogen is for those electrons. So what will happen is the electrons that these two guys have sort of agreed to share are going to sit closer to the chlorine than they are to the hydrogen. Here, they're both equally distanced. Here, chlorine is sort of digesting these more. This is known as a polar bond or a polar covalent bond, because it creates some sort of polar charge or an asymmetry within the molecule, right? Now, if you see this, do you see this little symbol here with the positive and this little symbol here with the negative? That is symbolizing the shift in electrons towards the chlorine. So if the electrons sit closer to chlorine, what charge does an electron hold? It holds a negative charge. So the chlorine is going to have an overall negative dipole moment or charge to it. The hydrogen, oh no, it's losing more than it really put into the whole system. So it's not getting quite as much electrons. So the hydrogen side of this will actually have sort of a positive side to it. And so that difference in charge, one side of the molecule being slightly positive, one side of the molecule being slightly negative, is what makes this molecule polar. This thing over here, because the electrons are shared equally, there's no dipole moment, or there's no difference in charge. It's sort of even balanced. So as far as nonpolar covalent bonds, a nonpolar covalent bonds occurs, it has to be two nonmetals because it's sharing covalent. They have an equal or an almost equal sharing of electrons because their electronegativity difference is very small. So usually the cutoff, some slides are different, I believe it's 0.4. So if the difference in electronegativity is 0.4 or less, we would say it's a nonpolar covalent bond, but we would say that their electronegativity is almost the same. They're just going to share them. So hydrogen and silicon, the electronegativity difference is 2.1 minus 1.8. Where those numbers came from, they came off of this, okay? You don't have to have those memorized. But the difference between that is a 0.3. We're going to say that that's close enough to call it a nonpolar covalent bond. Now, if we're a polar covalent bond, in this instance, this also occurs between two nonmetals. It has an unequal sharing of electrons, but it's still sharing the electrons. That's what makes it covalent. And it has a moderate electronegative difference in its charge. So oxygen and chlorine, we've got a 3.5 for the oxygen. That's how greedy it is. The chlorine is a greediness of 3. The difference is 0.5. If we're at 0.5 or greater, we're going to have a polar covalent bond, meaning that they are still, in fact, sharing the electrons. The difference isn't so great that they've transferred the electrons, but they're not sharing them equally. So polar covalent bonds because they don't share the electrons equally, the separation of the charge within the bond, or this sort of shift of a positive charge and a negative charge, is called a dipole. The positive and negative ends of the dipoles, we can see are, we're using this lowercase delta symbol, and it'll have a positive and a negative. And a lot of times you'll see an arrow written underneath it or next to the bond to symbolize the direction that the electrons are sort of shifting to. So it'll move from the positive to the negative side. So what this is saying is if we have a carbon bond and an oxygen bond, they are sharing the electrons, but the electrons are going to sit closer to the oxygen. Why are they going to sit closer to the oxygen? Again, if we go back to this chart, oxygen is 3.5, carbon is 2.5, so oxygen is greedier. Now, let's say that the electronegativity is, the difference in the electronegativities is really big. So one of the partners is super greedy for the electrons, the other guy doesn't really care a whole lot. And that cutoff is usually a difference of 1.8 or more. In that case, we're no longer dealing with a covalent bond. We're not sharing electrons. What's happening? We're just transferring the electrons. Okay, this happens between metals and nonmetals. The electron, if we look here, we've got potassium and chlorine. Potassium's electronegativity is 0.8, super tiny. Chlorine's is 3. The difference between those two is 2.2. It's such a great difference that potassium's like, whatever, chlorine, you can just have the electron. I don't want it. So the electron moves over. What do we get? A positive charge and a negative charge. We're not sharing electrons. We are sticking together because we have a difference in our charge. So the difference between the electronegativity, here we go. Yeah, I like this one. The difference in the electronegativity between two atoms will determine what type of bond we're going to get. So if it's 0.4 or less, they're sharing them, and we're going to say that they're sharing them equally. If the difference is between 0.4 and 1.8, they are still sharing the electrons, but there's an inequality or a polar covalent bond or a dipole moment happening. We've got a positive side and a negative side. And if we are in an ionic situation, the difference between the electronegativity is so great here that this guy just says, whatever, just take the electron. I don't want it. Okay, does that make sense? Those three different spaces? Okay. Now, electronegativities, again, you're not going to have memorized. I would give you the electronegativities. I would say, hey, here's some electronegativities for a couple different things. Tell me what type of bond it would produce. And you would say, oh, it's ionic, it's super different, or oh, it's nonpolar covalent. So here are some examples. We've got hydrogen, that would be shared equally, nonpolar covalent. Bromine and chlorine, super close in their electronegativities, so we would say that's also nonpolar covalent. HBr and HCl, two different acids here, hydrobromic acid and hydrochloric acid. The difference does create a dipole moment or a polar covalent bond. And then these guys here, those should be really easy to identify anyway. Yeah, between 0.0 and 0.4 will be, so we would take 0.4, wrap that into nonpolar covalent. Anything greater than 0.4, wrap that into polar covalent. So if it was 0.41, we would call that polar covalent, okay? As far as the ionic one's concerned, it's like you don't even really have to do the calculation, because if I look at this thing, I can already say that's going to be ionic. Why? Metal, non-metal. Easy to identify that. Cool. All right, so look at these and see if you can decide whether they are non-polar covalent, polar covalent, or ionic. And I know I don't have the sheet up, the electronegativities. So you can either look up the electronegativities on your phone or guess, see what happens. If you can get the concept of it, just say, oh, I think those are probably far enough from each other to be this or that. Okay, so for this first one, it's potassium and nitrogen. The difference between those two, if we were to calculate it out, is 2.2. That is definitely greater than the 1.8, so we would say it's ionic. I also can see that it is a metal and a non-metal, so I'm going to go with ionic. Nitrogen and oxygen, the difference between their electronegativity is 0.5, so that just beat the cutoff point for it to be a polar covalent bond. Chlorine and chlorine, I wouldn't even need the numbers for that because it's the same thing. So I know they're going to be equally greedy. Anytime you have a diatomic molecule, Cl2, O2, H2, whatever, those are all going to be nonpolar covalent. And then HCl, hydrochloric acid, there is a difference of 0.9, which is definitely within the range of polar covalent. So we're going to finish this section off. We skipped over 6.7. I'm going to finish off talking about attractive forces within a compound, because some of this stuff too will apply when we get into organic chemistry. So this is a protein string that is forming a helix. The reason that it forms this helix shape is because there is hydrogen bonding that's happening, or within the molecule, because there's like those dipole moments, or there's an unequal sharing of electrons. The hydrogen, which has got sort of a positive side, and the oxygen, which has got sort of a negative side, will stick to itself or attract itself, which gives it that curled shape. So let's talk about some of the different types of attractive forces within a molecule. We have dipole-dipole attractions and hydrogen bonds. So in a covalent bond or in a covalent compound in polar molecules, we have what's called a dipole-dipole attraction. So the dipole being that asymmetry in charge, right? Well, if I've got hydrochloric acid, the chlorine, the electrons stay closer to the chlorine. So the chlorine has sort of a negative charge here and then a positive charge by the hydrogen. So what will happen is that the adjacent molecule, the hydrogen on the adjacent molecule, which has sort of a positive side, will stick or attract itself to the negative side of the chlorine. This is one reason why polar things dissolve polar things, or likes dissolve likes. So hydrochloric acid, for instance, will dissolve in water because it's polar, and water is also polar. Water being the universal solvent has a polar structure. Things that are nonpolar won't dissolve in a polar material because they don't have that dipole moment. A specific type of dipole attraction, and that's what we have going on here, is known as a hydrogen bond, or actually, no, this is just a dipole-dipole attraction. But if you have a dipole attraction here and it contains hydrogen with fluorine, oxygen, nitrogen, and a lone pair on fluorine, oxygen, or nitrogen. So fluorine, oxygen, and nitrogen, if you see those with a hydrogen, that's known as a hydrogen bond. That one's like extra sticky. So it's got a dipole-dipole attraction, but it's sort of on steroids, okay? So this one here, because this is hydrogen with chlorine, it doesn't fall into that. So we would actually just classify this as a dipole-dipole attraction. If this happened to have been a fluorine, we would classify that as a hydrogen bond. Hydrogen bonds are the strongest force between molecules. So anytime we have a hydrogen bond, we know that the adjacent molecules are getting this very sticky quality to them. And that is one reason why DNA has that helix shape to it. Dispersion forces, this is a very light force, a very weak force between molecules. What happens is we've got, and you find dispersion forces in all molecules, okay? So whether it's nonpolar, polar, ionic, whatever. But what ends up happening is we get these temporary dipole moments. Or do you see how the nucleus here, it's sitting in the center and all the electrons are around it? This is like balanced and there's no charge to it. Well, that nucleus doesn't always sit perfectly in the center. Sometimes it will swing to one side and the electrons sort of get smushed or shoved to the other side of the probability sphere. In that case, the nucleus side will form a sort of a gentle positive charge and the electrons on the other side will form a negative. Now, this is a temporary thing. What would happen is, like they say here, we had two instances where nuclei were both sort of pushed to the left and electrons were pushed to the right. We'd get this dispersion force where these would attract to each other. But again, it's temporary because at some point that nucleus will settle back into the center or it'll move up or down and it'll attract or unattract to other molecules. So it's super weak, but makes it possible for nonpolar molecules to form liquids and solids. So something like, like methane, under certain circumstances, we can make that liquid, and or maybe something a little heavier like propane. We can make that a liquid. The reason that it can form a liquid or it can even stick to itself to become a liquid is because of these dispersion forces, but it's very volatile, right? So propane, you can smell it. It like volatilizes or turns into a gas really easily. So as far as how attractive forces relate to melting points, so melting points of a compound are related to the strength of the attractive forces between molecules or compounds. So if you have lower intermolecular forces, you're going to have a lower melting point. Weak forces would be dispersion forces. Stronger attractive forces like hydrogen bonding are going to have a higher temperature. And then the highest thing that you're going to get is an ionic compound. Ionic bonds have very, very strong forces because we're not even dealing with molecules when we're having an ionic structure. We're dealing with that lattice structure, right? So if we looked at sodium chloride, each sodium is connected to all the adjacent chlorines, making this three-dimensional lattice structure. So this structure is very, very strong. So these tend to have very high boiling and rather melting points. Think about how easy it is, trying to think of something that's a dispersion. Think about coconut oil. Okay, coconut oil is a non-polar material. The reason it's holding its shape is because of dispersion forces. How easy is it for your coconut oil to melt? Pretty easy. It depends on the day, right? Sometimes you go into the cabinet and it's liquid, sometimes it's solid. Versus table salt. I've never seen my table salt melt. Now, I have had a salt lamp that has liquefied before, and that's because the salt lamp is pulling moisture out of the air and it's dissolving the salt, but I've not actually seen salt melt before, change states like that. So here are some of the melting points. Look at what's going on for these ionics. 1248 degrees Celsius, 801 degrees Celsius. That's why you're not seeing your table salt melt, because you would need something much warmer than your oven. Here we've got some hydrogen bonds. So we've got hydrogen mixed with oxygen and hydrogen mixed with nitrogen. Again, if hydrogen was mixed with fluorine, we would also include this under hydrogen bonds. The melting point for these, not anywhere near as high as the ionics, but higher than the other ones because it's a pretty strong force, the hydrogen bonds. Dipole-dipole attractions that aren't including hydrogen and oxygen, nitrogen, or fluorine have a much lower melting point. And then these guys down here, these are nonpolar, right? So how are they even sticking together? They're only sticking together through dispersion forces because their nucleus is sort of getting knocked to one side and it creates a temporary dipole. These things are like barely holding together with their partners. So to melt that is super easy. You don't need a whole lot. So again, just that same idea, but written in a different way with some little pictures. So the weakest of our bonds are the dispersion forces. That's just a temporary asymmetry happening. Then we move to a dipole-dipole, which is where we have two nonmetals. that are sharing the electrons unequally. Then we have hydrogen bonding, which has to be hydrogen with F, O, or N. Then we've got our ionic stuff up here. Okay, so looking at these, identify the main type of attractive forces that are present in the liquids of the following compounds. So we have ionic bonds, dipole, hydrogen, or dispersion bonds. So I want you to tell me for each of these bonds, which one of those is present. And they all have dispersion, okay? So you don't have to write dispersion for all of them. They all have that. But if it's the only one that they have, write dispersion. Okay, so identify the main types of attractive forces that are present. So between N and Cl, this is a polar covalent bond, so they're not sharing the electrons equally. So that would give us a dipole-dipole force. H2O, this is a situation where the hydrogens and oxygens, they're not sharing the electrons equally, but the difference between hydrogen and oxygen is so great that we're going to go with a hydrogen bond. Anytime you have two of the same thing, dispersion forces is the only thing that you're going to see. So those nonpolar covalent bonds just have temporary dispersion forces. That's a metal and a non-metal, so we can go with ionic bond. And then here we've got hydrogen and nitrogen. Again, anytime hydrogen is with nitrogen, oxygen, or fluorine, we call that a hydrogen bond. Okay, that's it. That's all I've got. So we are, I'm going to pull up our schedule real quick. There we are. Yeah, we're good. I don't want to start chapter 7 yet. We've got more than enough time for chapter 7. What we may end up doing, I'm not going to move the test, the second test, but I may start lecturing a little bit early on chapter 5 and just move some of these up so we have a little bit more time with solutions and acids and bases. Yeah, but we're good right now. So that's all I have specifically for you. If you have specific questions, stay around, ask me. Can we do some more examples? Specifically of what, Lauren? We can definitely do more examples. Lauren, is there specifically, what do you want to do more examples of? Do you want to do more examples of like the dipole bonds, like the dispersion, dipole, those sorts of things? Okay. Yeah, we can definitely do some more of those. If you're good and you're done with me, a little confused on how to tell which force it is, Courtney. Okay, yeah, great. Let's do a couple more. If you're done with me though, you're free to go. Okay, so when looking, just to review this, so when we're identifying ionic bonds, that is going to be anytime it's between a metal and a non-metal. Okay, so metal. Hi, Abigail. And non-metal. All right, hydrogen bonds are going to be a molecule that is hydrogen with oxygen, hydrogen with fluorine, or hydrogen with nitrogen. Okay, that's what will fall under this. A dipole-dipole attraction is two nonmetals, and it has to be a polar bond. Or it has to be a situation where their electronegativity, the difference in electronegativity is greater than 0.4. Okay, so H and Br, HCl, we wouldn't classify these under this field because the electronegativity isn't, or because it's not hydrogen with one of these things here. Dispersion forces are when we are looking at two nonmetals, and they are a nonpolar covalent bond. So dispersion force put with nonpolars, dipole-dipole put with polar covalent bonds, hydrogen put with polar covalent, but it has to be one of these situations. It has to be oxygen, fluorine, nitrogen, and then this is just a metal and a nonmetal. So I'll give you a couple of examples. Oh, come on, there we go. Oh, doesn't want me to exit the slides. Okay. Yeah, I'm a little confused on how to tell which force it is. What was that last dispersion one? Dispersion is two nonmetals that have a nonpolar covalent bond. So they have to have a very similar electronegativity, meaning that they're sharing the electrons equally, which means that they only get temporary dipoles. And those temporary dipoles or asymmetries are a dispersion force. Does that clear it up, Courtney? Okay. So what do we have here? We've got F2, Al2O3, HI, MgO, OH minus, and no. H, F, Okay, so tell me two things. Tell me what the bond is, and then tell me what the force is. Electronegativities will be in the PowerPoint. They should be in your textbook, or you can literally type into Google like electronegativity sheet or charge, and you can pull one up that way. All right, so the first one here, the type of bond that we have going on is a nonpolar covalent bond. Why? Because each of the fluorines are sharing the electrons equally, right? So when we have a nonpolar covalent bond and the electrons are shared equally, the only force that we're going to have is a dispersion force. And that's when we're going to temporarily have a electron, or the nucleus and the electron form a temporary dipole where they can stick together. Here, this is ionic. So the force is also ionic. This is the strongest. This here, we have a polar covalent bond. So they are sharing the electrons. They're both nonmetals. They're not sharing them equally. But it's not a hydrogen bond because hydrogen is connected with iodine here. So this is a polar covalent bond, and it's going to be a dipole force. This here is ionic, so its force is also ionic. This one here, this is between oxygen and hydrogen, so this is a polar covalent bond. As far as the forces that's happening, though, it's hydrogen with oxygen. So not only is it a polar covalent bond, but we also have hydrogen combining with oxygen, which makes it extra strong, or a hydrogen bond. HF is also polar covalent. The H and the F, remember, hydrogen combined with fluorine, oxygen, or nitrogen also will give us a hydrogen bond. Of these, Strongest is going to be this and this. Next strong will be this and this. Next will be this, and then this thing here, 4, is the weakest of the forces. We only use polar and nonpolar when we're dealing with molecular or covalent bonds. So we don't classify this as polar. It's only when it's between two nonmetals that we use the polar and the nonpolar description. Does that make sense, Courtney? You kind of want to think of it. Okay. Yeah, you kind of want to think of it like if we were to draw let's clear this whole thing out. We were to draw like up here, you know, compounds. We would divide it into ionic or covalent. From here, we could divide it into polar or nonpolar. Okay. Polar can be either hydrogen bond or dipole. Dipole. Nonpolar is going to just give us dispersion. And then ionic it's an ionic force. Does that make a little more sense? So this sort of stuff over here doesn't even come into play at all over here. Any other questions? Let me write that down. Okay. Sorry, it's a total mess. So yeah, first breaking them up into covalent or ionic. And sometimes you'll see the word covalent instead of covalent. Instead of covalent, you'll see it as molecular. But in this case, we're sharing electrons. In this case, we're transferring. Hello. All right. Any other questions? All right. So I'll leave this up for a minute, Courtney, so you can finish copying it. Otherwise, we are good to go for the week. Awesome. If you want to have some smiles or shed some tears, the vice presidential debate is on this evening. So,
oh, hi.
Okay, hold on one sec. So yeah, if you're done with me though, check out so that I can chat with people individually for questions. All right. Thanks for coming. And Monday's video, please. Yes, Courtney, I'll do that as soon as I get off. Okay. Cool. Bye.